Guys, this is the final but not the least part of my smart energy meter. So in my hand you can see there is a clamp meter. Now I am going to set this value to 200 amps AC. Now I am going to clamp this clamp meter here. You can see here I had made 10 primary turns for the YHDC 100 amps to 50 milliamps. So now the final configuration is 10 amps to 500 milliamps because my MCB is rated 10 amps. So I had to make some adjustment. So this is the live wire and neutral wire of single phase AC coming from the grid of West Bengal State Electricity Distribution Board. Now you can see our power consumption is 0.2 to 0.3 amps. So here in this coil it increases 10 times for this current sensor, and this current sensor goes through this wooden plank gap. From this wooden plank gap through this hole, here is that energy meter. It runs all the way down this tin. From this gap to my laptop. From here comes that SCT013 output wires, and I had fed this to our Arduino via, where are those resistance? Yes, it is here, via this 33 ohms 1 watt burden resistance with this 10 kilo ohms quarter watt voltage divider resistance with this, along with what are the values, 250 volt 8.2 UF electrolytic capacitor. So here is the explanation of the circuit diagram. You can see these are the live and neutral of SCT013 100 amps to 50 milliamps, that current sensor, and these 2 points are connected in parallel with this 33 ohms 1 watt resistance. Here is it, and one of the terminals goes to the analog input of A0 and other terminal goes to the midpoint of this 10k quarter watt resistance connected in series. So here I had supplied 5 volt from Arduino VCC, and this is the common ground, and here this is a symbol of electrolytic capacitor that's marked as 250 volt 8.5 UF, but I recommend you to use anything between 10 UF to 100 UF for more precise filtering. Here I get 2.5 volt midpoint because this output voltage is fluctuating. Sometimes it is beyond the threshold limit of Arduino's analog input, so I had to make it stable to 2.5 volts safely. And in my case SCT013 100 amperes to 50 milliamps is modified as 10 amperes to 5 ampere or 500 milliamps by making 1 mm 10 number of primary turns. And some more modification is here, like I am using this D0, D10 and D11 digital pins to feed data to this Bluetooth low power module, so that I can assess my readings on my mobile phone screen. Let me show you. Here is the code. You can find this code on my video description. here in serial monitor I had shown only the power consumption in terms of P and IRMS, but in Bluetooth, let me clear the screen. You can see the everything in details, like supply voltage 240 volt 50 hertz AC, that is constant. Power consumption is near about 120 watt or 120 to 126 watt max, but giving average of 123 watt, and the bill in rupees is 0.87 roughly. Here are the electrical formulas. Double power equals to IRMS into 240, that is the supply voltage, and here is the computerized formula for the EMON package, energy library monitoring package, that is emon1.cal IRMS 1480. 1480 is actually the number of times we are calculating the RMS, which is actually near the value of √2. If you take it as a whole number, 1414 roughly, it is this thing. But you can change this 1480 according to your need for calibration, but I recommend it you to keep this value fixed and change the power factor or gain, that is this highlighted 4. You can change it according to your constant load, but I recommend you to keep this 1480 constant. So let me explain what are these 128 watt load running. So first comes to my heavy load, that is the ceiling fan. It is near about 65 watt. Then comes this small LED tube, that is 5 watt. 65 plus 5 70 plus 40 watt this fluorescent lamp, so it gives near about 110 plus this laptop charger, that is right now consuming less than 2 watt. Here I have an indicator that is also consuming near about 1 watt, and this Wi-Fi adapter that consumes about 1 watt. So roughly $110 for the heavy load of fan, plus this small tube plus this bigger one fluorescent tube, 110 watt, and remaining this dummy load like this laptop charger, Wi-Fi router, plus ohmic loss because of our conductors. So this is more or less accurate.